So now we're at the last chapter, and it's got a couple of parts. Part 1 is something called correlation. Up here, correlation. So co means with, relation or with or to. Correlation means how two things are related to one another. We need to start by differentiating the word correlation from the word causation. Just because two things happen at the same time every day doesn't mean that they were both caused by the same thing. Just because you and somebody always walk out the room of your class exactly the same time every day doesn't mean that there's causation. There means there's correlation. You're both in the room, you both walk out at the same time because the class is over. The cause of you walking out the room is the class is over. The fact that you walk out together is correlation. You're sitting near each other, whatever. You don't necessarily decide that you're always going to walk out in front of that person. So correlation just means two things move together. It's sunny outside and it's hot outside. Okay. Correlation or causation. Well, maybe the sunny caused the heat. Maybe the... Okay? Two things can be related without necessarily one causing the other. We have to think about or have a theory about when something is a cause of something else. But they could be related without having a cause. Okay? So correlation just means two or more variables move in predictable ways. Causation means one variable is caused to occur by the other variables or variables. So again, correlation just means two things move together. If we look at the price of gas over time and the number of people on the internet, and we draw a graph, we'll find that they're correlated. Price of gas does not cause people on the internet, probably. Okay? Just because they're correlated doesn't mean that they cause each other. Okay, so how do we figure this out? How do we calculate this thing called the correlation? So we have a set of numbers. We want to see if they're correlated. Well, it's a multi-step process, and the first step is to find something called the covariance. Co means, again, with, the variance with each other. So remember back a long time ago, we figured out how to calculate the variance, and this is the formula to calculate the variance. Okay? So the variance of x is the sum of x minus x bar squared over n, which you could write out and say is also the sum of x minus x bar times x minus x bar, right? That's what squared means, over n. But now we're interested in looking at how two variables relate to each other. So all we're going to do is get rid of this part, and instead of that, we're going to do this. So we're going to say, we're going to find the sum of x minus x bar times y minus y bar. And again, x bar and y bar are the mean of x and the mean of y. Right? The mean of x or the mean of y, again, divided by how many observations we have. So we're going to call this the covariance, and that just gets abbreviated COV. There's no letter for the covariance. Covariance of x and y is x minus x bar times y minus y bar. Now you're saying, what does that tell us? Well, let's think for a second. Let's suppose we have what's called a direct relationship. And a direct relationship means that as x goes up, y goes up. Okay? So we may believe that as nutrition goes up, people get taller. So x would be how many calories they ingest when they're a kid, and y would be how tall they are. Okay? If x is low, if the amount of food we eat is low, then we're going to end up short. So x would be below average and y would be below average. So x minus x bar would be a negative number. Y minus y bar would be a negative number. We multiply those together, a negative times a negative, and we get a positive. On the other hand, somebody who eats a lot ends up being tall. That means if x is above average, y is above average. So x minus x bar is positive, y minus y bar is positive. We multiply those together, and we have a positive number. Okay? Let's think of what happens if we have what we call an inverse relationship. An inverse relationship means when x goes up, y goes down. So x is the price of gas, and y is how much gas we buy. Okay? So if the price of gas is low, x is below x bar, the quantity of gas we buy will be high, y is above y bar. So x minus x bar would be negative, y minus y bar would be positive. We multiply those together, we get a negative number. If the price of gas is really high, x is above x bar, then we're going to buy less gas, y will be below y bar. X minus x bar will be positive, y minus y bar will be negative. We multiply the positive times a negative, and we get a negative. So this thing, this covariance, if these two variables move together, it's going to be positive. If they move opposite from each other, what we would call inverse, it's going to be negative. So this is very helpful to us. Okay? So, again, just talked about this. If it's negative, that means there's an inverse relationship. This kind of relationship will give us a negative covariance. That kind of relationship will give us a positive covariance. Now, when we calculate the covariance, we get a number. That number, in this case, doesn't tell us anything. We're going to use it to calculate something else, but the number by itself doesn't mean anything. So, we're going to use that covariance to calculate something called the coefficient of correlation. And the coefficient of correlation is given the letter r, the little r. Now you're saying to yourself, I think I just noticed something. And you should have noticed something. Covariance doesn't get its own letter, just a COV. That tells you it's not very important. What does have its own letter? Well, S does, the standard deviation does, R does, the coefficient of correlation. The variance is S squared, so it's going to be less important than the standard deviation because it has a letter, but it's borrowing the letter from the standard deviation. We can tell how important things are by whether or not they have their own letters. So this coefficient of correlation is going to be pretty important because it has its own letter. So the correlation of x and y is going to be equal to the covariance of x and y divided by the standard deviation of x and the standard deviation of y. And again, we'll do an example here in a second. Turns out that means that r is somewhere between -1 and +1. If r is -1, that means we have a perfect relationship, and we'll talk about what that means, but perfectly inverse. If r is +1, that means we have a perfect relationship, and it's perfect direct. And again, we'll talk about what that means in a second, but -1 to +1. So here we have a set of numbers, x and y. X goes 2, 4, 6, 8. 1 goes 1, 2, 3, 4. So we know what this is, right? Y is always half of x. Y is half of x. Y is half of x. Y is half of x. Okay? That means this is a perfect relationship. Perfect. Okay? Something you wish you had in life, a perfect relationship. If I know x, I know y exactly. That's a perfect relationship. If I know x, I can figure out exactly what y is and never be wrong. Okay? Perfect relationship. And in this case, again, y is half of x. So what we want to do now is figure out what the coefficient of correlation is, and the correlation coefficient of these two numbers, sets of numbers, should be 1. We need to do a calculation which will generate the number 1. The number 1 will tell us that this is a perfect direct relationship. So the step number 1 to do this is we need to calculate the covariance. So come back over here. This has a mean x bar is 5. y bar, the mean of these four numbers, is 2.5. Okay? So we're going to take 2 minus 5 times 1 minus 2.5. Okay? And we're going to take 4 minus 5, 2 minus 2.5. We got it? And we're going to do that 4 times, and we're going to add them up. Okay? So here it is all written out. 2 minus 5, juniors 5, 3 minus juniors. So we're going to subtract each of the x's, 5, 2.5 subtracted from the y's. Do the math. We get 4.5, 0, 0.5, 0.5, 4.5. Notice they're all positive. They're all positive because we have a direct relationship. We add those up. We get 10. Okay? We take 10 divided by the fact there's 4 numbers. 1, 2, 3, 4. 10 divided by 4 is 2.5. That's the covariance. The covariance is positive. That means it's a direct relationship, but it's not telling us anything else. What we need to do now is calculate the standard deviation. So we have the standard deviation of x that we calculated, the standard deviation of y that we calculated, and again, we just had Excel calculated for us. If we do the math, little r, the correlation coefficient, is 2.5, which is the covariance. That's the covariance. Divided by that and that. And turns out if we do that math, we get 1, which tells us that the correlation is perfect. There's a perfect positive relationship between x and y, which we knew because x divided by 2 is equal to y. Okay? So it's a perfect direct relationship. If it had been -1, it would be perfect inverse. If it's 0, that means there's no relationship. Okay? 0 means that if we know x, we can't tell anything about y. It's just random. So here's the graph of the numbers we just did. It's a perfect direct relationship. In other words, it's a beautiful straight line. That's the graph of the numbers we just calculated. Okay? So let's look at these numbers. Notice 1, 2, 3, 4, 2, 5, 5, 8. So that's twice that. That's twice that. But that one's a little more than twice, and that one's a little less than twice. Is not perfect. It's good, but it's not perfect. And if we do the math here, we get a correlation of 0.948. 1 would be perfect. 0.948 is close to 1. It's telling us we can mostly figure out y if we know x, but not exactly. If it were exact, it'd be 1. It's a little less than 1. It's telling us if we know x, we can mostly figure out what y is, but not exactly. Okay? And again, if we draw a graph here of this now, it's not a straight line, it's a curvy thing or crooked thing, and that tells us it's imperfect. Okay? So here's another one. Now we have 1, 2, 3, 4. We've got 2, 5, 5, 3. Now that is twice. That's a little more than twice. That's a little less than twice. That's not even 1th. So if we look at this, we go, hey, it's not much of a relationship. I can't predict y from knowing x, and I get a correlation coefficient that's pretty close to 0. 0 means no relationship, so 0.25 means there's hardly any relationship, but there's maybe a little relationship. If I draw the graph of this, it looks like this. There's no way, okay? But, so if I draw a straight line through here, I'm going to get something like that, and it really doesn't tell me anything. It's kind of flat. There's one problem here, and the problem is that this correlation coefficient only works on data that are a straight line. What would happen if the data actually look like that? In other words, we could have data that actually were perfect, and it's just curvy. Okay? We wouldn't pick that up because correlation coefficients only work on straight lines. Okay? So here's another one. X goes 1, 2, 3, 4. Y goes down 2, down 3, down 3 as x goes up by 1. So I can mostly predict what y is going to be. Y is going to go, every time x goes up by 1, y is going to go down by 2 or 3. I can kind of predict what's going to happen to y. But it's inverse. This is going up as this is going down, right? X is going up, y is going down. I get a negative sign if I do the math here. And 0.988 tells me I kind of mostly know, but I don't completely know. Okay? If I draw a graph of it, it looks like that. It's close to a straight line, but it's not really a straight line. All right? And again, straight line. Look at x and y here. Take 1 squared, I get 1. Take 2 squared, I get 4. 3 squared, I get 9. 4 squared, I get 16. This is a perfect relationship. But because it's a curvy relationship, if I graph this, it looks like that. Correlation tells me that it's not perfect because correlation is trying to put a straight line through this curve, and it doesn't make any sense. Okay? All right, so let me just give you a real-world example of this, and we'll come back over time and play with some more. The Las Vegas Chamber of Commerce paid a consultant to study the relationship between the money spent on schools and student performance in the high school. What they found was low correlation. They did correlations, and therefore they concluded that spending more money does not improve schools. Is that right or wrong? Well, the answer is we have no idea. Correlations never tell us causation. They only tell us if things move together. So that study in no way had anything to do with whether or not the money spent on the school actually helped the performance. What it said was, if I looked at the total amount of money spent on the school and total overall student performance in that school, there wasn't a lot of correlation. They didn't move together. Okay? That doesn't tell us that there's causation. Okay? It may be that there's more going on there, that this is complex. It may be that it is, and that spending money doesn't help. You don't know, because correlation is just about the movement together. It's not about an explanation. We don't know about causation. We can't explain it. There's another technique which we're going to learn, which is our next video, which might be able to tell us whether these things are causal, whether actually spending more money affects the school. But correlation coefficients don't. And the Las Vegas Chamber of Commerce spent 5 figures hiring this consultant who did nothing, and somehow the Las Vegas Chamber of Commerce didn't realize that they did nothing.